to establish angles or shifts at joints. Okay, so the first question is whether this task is simple or difficult. Of course, forward kinematics, despite all the details how to calculate the forward kinematics, finally, it is quite a simple task. Why? Because finally we will obtain a closed form formula to describe position and orientation. And the forward kinematics means just to plug, I'm sorry, just to plug into the equations appropriate data, and finally we will obtain position and orientation. So it is very simple and very technical. Unfortunately, inverse kinematics is much more complicated. Why? Because the mapping, usually, as you know, because we have done a few examples, the mapping is highly nonlinear. You can see sinuses, cosinuses of some angles or sum of angles. So the formulas are really complicated, and when dimensionality of configuration space grows, so the complication of equations grows rapidly. A lot of terms, a lot of complicated expressions. So generally, the mapping, despite the fact that they cannot be can be derived. So the inverse kinematics is much more complicated. And I've presented at least three methods. The first one was geometrical in nature, and it was illustrated on example of double planar pendulum. So generally, this method relies on some geometrical facts from planar geometry, usually cosinus theorem. And based on that, we can obtain inverse kinematics in closed form formulas. Unfortunately, this method works only for very simple robotic structures. So usefulness of this method is really, small. The other method discussed, or other idea of the method, was kinematic decoupling. I didn't discuss this method with details, but generally the method tries to decompose complicated task of position and orientation into two separate subtasks. One for orientation and one for position. And instead of solving a single task, we solve two tasks, but of course in a smaller dimension, and therefore the tasks or subtasks are much more easier to solve than the original one. But also this method cannot be applied to any manipulator, because it works only for the case when the last three axes of motion crosses at a single point. And of course, not all manipulators satisfy this property. And finally, I've discussed or started to discuss the method which is useful and frequently used in robotics, which is called Jacobian based method, because it is a whole family of methods. And Unfortunately, this method is numerical in nature, so the solution of inverse kinematics is performed in repeating some steps, but it works for any manipulator. And let's recall what we have obtained. So the first step, maybe not the first step, but the initial form was forward kinematics. We have, maybe given one, forward kinematics, second, initial configuration. Here, subscript iteration counter. So at initial configuration, we set iteration counter to 0, and 3 XF. So final, or sometimes it is called goal point. Okay, and we need to find such Q star such that if we plug Q star into this, so K on Q star is equal to XF. And I've presented how to derive so-called Newton algorithm of inverse kinematics. It is described like this. So the next configuration is the current configuration plus psi positive and small real number. Of course, we select the number. Here we have Jacobi matrix evaluated at current configuration and multiplied by XF minus K on QI, like this. Of course, this method, Newton algorithm of inverse kinematics, I will add for non-redundant manipulators. Non-redundant manipulators, it means that M is equal to M. So dimensionality of Q is equal to M, dimensionality of X is equal to M. So the manipulator is non-redundant. And so let's draw a small picture once again. We have a manipulator. The manipulator is at current configuration. So there are and we have here a point. The point here is K on QI. So according to the angles at joints and some length of links, we can calculate this point. And XF, let's say it is here, XF, it is our goal point. And the method is based on sequential approaching along this line from this point to this. Okay, this coefficient influences how fast we go along this line. And of course, here you can see two contradictory facts. The first one is if we set xi too small, so we need to perform a lot of steps to converge this algorithm. So we make a lot of very short motions along this line. So if we set xi too big, so in this case, the behavior could be, and usually is, very chaotic. So we will not move along this line. So we can skip, for example, here, here, and here. So it is very dangerous. So usually we take relatively small values of xi. Let's assume so xi 10 to minus 3, for example. So it is really, really small value. And as can you see, based on previous configuration and the Jacobi matrix, let's recall what is Jacobi matrix. Jacobi matrix is a partial derivative of kinematics with respect to configuration. And based on the Jacobi matrix or its inverse, and what is this? It is just the distance. This is just this vector. Okay. Okay. And xi means scaling the vector. So xi xf minus k on qi. Okay. So probably we stopped somewhere here, and we've discussed when the algorithm should be stopped. Okay, so the idea is quite simple. We need to stop generating consecutive configuration at such situation when our end of effector is close enough to xf. So let's conclude this. The algorithm is completed when end effector is close to the goal point. If you need mathematical formulation for this fact, it is quite simple, because we calculate distance. So we take the length of this vector, and if the length is smaller than given accuracy, so we stop our calculations. Okay, so let's continue. We have two problems. Two problems. The first one is what to do when manipulator is redundant. So in this case, dimensionality of the configuration space is smaller than dimensionality of configuration space. And as you know, Jacobi matrix is a matrix of the size m by n, so row, number of rows, number of columns. Okay, so as can you see, in this case, the matrix is rectangular, not a square like here in the previous case. So if we have a closer look on this formula, here you can see inverse of a matrix. If a matrix is square, so we have a chance to invert it. But in this case, probably you don't know how to invert a rectangular matrix. Of course, we will discuss this case in our future comments. And the second problem is the following. The problem of inverting. As can you see here, I need to invert the matrix. You know that if you have a matrix, any matrix, some matrices, I mean square matrices, can be inverted, but other matrices cannot be inverted. So what to do when, let's say, some matrices, let's JQ, for example, cannot be inverted. So the two problems should be solved. So let's start with the first problem. What to do when manipulator is redundant? So let's start with intuitive example. So maybe not too realistic, but for illustration purposes, it is quite good. Let us assume that we have two-dimensional space, configuration space, Q1 and Q2. I will draw it, Q1 and Q2. Let us assume that our kinematics is very, so as can you see, dimensionality of Q is equal to 2. And we have a single component in forward kinematics. Let's call it, let's say, minus Q1 plus Q2 maybe like this. Okay. Oh, plus 1. Okay. So we have a form. So dimensionality of x is equal to 1. Okay. And let's try to solve the following task, inverse task. Let us assume that xf, so the goal point using these kinematics, is equal to, let's say, 3, for example. So what we have the following. Based on that and that, we conclude that 3 minus Q1 plus Q2 plus 1. So Q2 is equal to 2 plus Q1. So we obtain the following relationship. So let's draw a picture So let's draw all points in the configuration space which satisfy this equation. So for Q1 equal to 0, so we have here point, so 1, 2, 0, 1, 2. If we have Q2, so probably it will be 4. If he will be, so let's okay, so I've drawn all solution of inverse kinematics problem for this very simple example. So, but what we need to do, our goal was to find Q star. So Q1 star and Q2 star. As can you see, we have a lot of choices, a lot of points. All the points belonging to this line satisfy these equations or are solution of this particular problem. So maybe I will ask you for help. So please tell me which point should I select according to some criterion? Any idea? Which, because I have a lot, infinite number of points in this line, and each one of them is good because it satisfies this equation. So which one, because I need only a single one. So which one is the best with some criterion? So you need to think about criterion, and based on this criterion, you can get the solution, so a single point. An idea? No one can help me? So if not, so I will propose a solution. The solution is the following. Let's try to find such a point which is as close as possible to the origin of this frame. So this point is at some distance, this point is at some distance, this also, and this also. But can you see that there is a single point like this, which is closest to this origin of this frame, and this one would be our selection. Why? Because it is optimal to some criterion. As can you see, the solution is very effective, very small one, because as can you see, if we prolong this line, so we can get probably infinite values of Q1 and Q2 maybe here, okay? But this one is very nice, very minimal, and therefore we will select it. And let's conclude. For non-redundant, for a redundant manipulator, like in this case, because dimensionality of Q is bigger than dimensionality of X, we have infinite number of solutions. Therefore, we need to set on the solution some criterion, some minimality criterion, and select only a single solution. So it was example, but how to do it in practice? I will just present Newton algorithm of inverse kinematics for redundant manipulators. M is smaller than n. And the, the shape, general shape of this algorithm is very similar to the previous one. So let's compare it. So the initial data are exactly the same. Here was inverse of Jacobi matrix. Of course, in this case, we cannot make any inverses. So we draw like this. And the rest remains the same as previously. So what is this? J hash is pseudo inversion of J matrix. So how calculate pseudo inversion? Well, the formula is quite simple because it's like this. Jacobi transpose. I've omitted arguments just not to make too much math in this formulation. So Jacobi transpose inverse, pseudo inverse of Jacobi matrix looks like this. So let's have a look. So at first we need to start with discussing dimensionality of this. So let's start with this. Because J matrix is M by N, so Jacobi transpose is N by M. So we have here N by M matrix, here M by N, and here N by M. So as can you see, if we multiply the matrices, we will obtain a square matrix M by M. So square matrix, possibly we can invert. So inversion of matrix leaves the size of result the same as argument. So we have M by N, and coupling this and this together, we conclude that J hash is a matrix of the size N by M. And as can you see, it is you can deduce this in other way. So here we have a vector N by 1, this vector N by 1, this vector, because it lives in a task space, is M by 1. Scalar is a matrix 1 by 1, so it must be N by M, okay? Because the result must be N by 1, and M in this multiplication disappears. Okay, so let's compare the Newton algorithm for redundant manipulator with Newton algorithm for non-redundant. So can you see this, and this is the same? The only difference is that for non-redundant manipulators, we invert Jacobi matrix directly, But in this case, because Jacobi matrix is rectangular, we cannot do it directly, but we apply pseudo-inversion, which generally prefers the shortest solutions, like here. And the formula is almost the same. Instead of inverse here is pseudo-inverse here. So we have solved the first problem, what to do when manipulator is redundant. So the solution is, instead of using this algorithm, we are using this algorithm. So let's move to the second problem. What to do when matrices cannot be inverted? Please notice that in this algorithm, we need to assume that the matrix is invertible, but what to do when the assumption isn't satisfied? And also in this algorithm, as can you see, in definition of pseudo-inverse is a matrix inversion. So the same problem appears, inverting of some matrices. And we will address this problem in a while. Okay. But before doing that, in robotics, we define so-called manipulability matrix. It is just a matrix appearing here. So it is Jacobi matrix multiplied by its transpose. And based on manipulability matrix, we define manipulability index. So usually it is, of course, because the matrix depends on Q, so manipulability index should also depend on Q, and it is equal to square root of determinant of this matrix. And what for we define this? Because it has a clear physical meaning, which will be explained a little bit later. So roughly speaking, the manipulability matrix can be defined for any manipulator, redundant or non-redundant, doesn't matter. And based on that, we can also define manipulability index. And as can you see, manipulability index is 0. This value gets the value of 0 when this matrix cannot be inverted. So it is quite visible sign that some matrices cannot be inverted. So we just examine manipulability index, and in this case we can be sure that the formula cannot be applied. Okay, so let's address the second question. the matrices cannot be what to do. So before answering this question, let's characterize the configuration when this situation happens. So we define oh, maybe not like this. Let's calculate rank of Jacobi matrix. So before doing that, so let's because probably this concept is known for you from basic course of mathematics. So let's start with 2 or maybe 3 very simple examples. Well, example number 1. We have a matrix. Let's calculate not depending on Q, but a matrix with some numerical data. Well, let's generate randomly almost -2, 1. Okay. So I have a matrix, and the question is, what is rank of this matrix? Let's call this matrix A, for example. What's the rank of a matrix? What's the definition of rank? So this matrix is, as can you see, 2 by 3. So rank of a matrix is such a number when I select from a given matrix some submatrix. Let's call rank R is equal to R, and R is such a number that when I select a submatrix of A of the size R by R with non-zero determinant. So let's check how it works in this case. So as can you see, oh, maybe I will need to add, and R must be maximal value. Okay, so the first question is how big a square matrix can be selected from this matrix? So, any idea? Please help me, please. No one knows? Can you hear me at least?
2 by 2?
Yes, for sure. Why? Because I select maximum value from this. Okay, so maximum matrix is 2 by 2. In robotics, we always have the number of rows is smaller or equal to number of columns. So in robotics, we have the first index is the maximum. So what we need to do, we need to check whether exists such a matrix 2 by 2 with non-zero determinant. Please notice that I have a lot of choices. I can select, for example, this submatrix. Can you see? I can select this matrix, submatrix, but also I can select such submatrix. Okay. So, and if I will find a single submatrix, so with determinant non-zero, so I don't need to check any other submatrices. So let's take, for example, this matrix 0, -2, 0, 1. Determinant of this, as can you see, is 0. So no, but I have more choices. I need to select if this test fails, so I need to check other possibilities. So let's check the green possibility, for example. And I have, as can I see, 2, and it is equal to, not equal to 0, so yes. So R is equal to 2. So the rank of this matrix is equal to 2 in this case. Example number 2. Let's modify this matrix a little bit. And like this, maybe 0, -2, 0, -4, and 0, 1. Okay. And once again, I'm asking what is the rank of this matrix. So as can you see, we need to check all the possible submatrices of 2 by 2. So 0, -2, 0, -4. Determinant is equal to 0. Determinant of 0, -2, 0, 1 is also 0, and determinant of 0, -4, 0, 1 is also equal to 0. So what is the conclusion? The conclusion is that rank of this matrix isn't equal to 2. Why? Because I've selected all 2 by 2 matrices and all of them has determinants equal to 0. So maybe I need to check whether R is equal to 1. So I select submatrices 1 by 1. So this submatrix, please notice that the scalar is 1 by 1 submatrix. This, and this. And as can you see, rank of this matrix, this A matrix, is equal to 1, because, for example, this item isn't equal to 0. Okay? And example number 3. Let's make another matrix A very bad matrix, and we try to find rank of this matrix. For sure, if I select any 2 by 2 matrices, determinant is equal to 0. If I take any 1 by 1 matrix, it is also equal to 0. So the rank of this matrix is equal to 0. Okay? So you know the definition of rank of a matrix. If you have a matrix, you can doing some simple calculation. You can get rank of a matrix. Of course, in robotic terms, the matrices aren't composed of numbers, but it is a Jacobi matrix, and the matrix is items are some expressions, okay? But nevertheless, if I plug particular configuration, which isn't which is composed of some shifts or angles, so the Q is fixed. So also this matrix is fixed. So let's, based on that, let's define the main concept. So maybe like this. Configuration Q is regular when a rank of Jacobi matrix at this configuration is maximum. So it is equal to M. Let's recall that Jacobi matrix is M by N, and M is, so it is maximum possible. Okay, so configuration Q is regular when this equality holds, but configuration is singular when, of course, rank of Jacobi matrix is smaller than maximum possible. So it is smaller than N. So introducing the two terms, we can, using this language, we can once again go back to our Newton algorithm. And for example, we can say that this algorithm will be completed without any problems when we cannot encounter such configuration Qi, which is singular, okay? Or in other words, the algorithm works well for regular configuration. Why? Because in this case, we will not have problems with inverting this, because the rank of this matrix is full. So in this case, the matrix is invertible. So we just plug the data and calculate consecutive configurations. Okay, the same can be said in the case of this algorithm. Okay, if we have no problems, if we have regular configurations, so this matrix all the time is invertible, and the algorithm iteratively allows us to obtain desired Q star configuration. Okay. Of course, we will calculate singular configurations because why the singular configurations are so bad in robotics? Because if we are at singular configuration, the rank of Jacobi matrix drops below its maximum value, and we cannot directly apply this or the previous algorithm because we will encounter a problem with inverting the matrices. Example, so what's problem with inverting matrices? Let's make the simplest possible matrix. So the matrix 1 by 1. And if we want to inverse this matrix, so as can you see, it could be infinity. So plus or minus. So we will encounter numerical problems if we try to apply directly the algorithms this or the previous one directly. So let's make a few examples. The first example, very standard. Double pendulum, planar. As you know, we have Q1, Q2, A1, A2. I have X, I have Y. And as you know, C1 is cosinus of Q1. Sinus of Q1 plus Q2. Okay, so I have a kinematics. So dimensionality of X is equal to 2 because I have two components. Dimensionality of Q is also 2 because Q is composed of Q1 and Q2. So this manipulator is non-redundant. So let's calculate Jacobi matrix. Now we need to take derivatives. Like this. General, it is general statement. In our case, we have like this. So for this particular manipulator, we have Jacobi matrix, which is equal to minus A1 C1 can you see I've took this expression and take derivative with respect to Q1. So the result is here. And once again, with respect to Q2, the result would be like this. And the second row, I take K2, so this expression, and once again take derivatives. I will obtain A1 C1 plus A2 C1 2 and A2 C1, 2. Okay. So how to get rank of this matrix? So in this case, it's relatively simple. I need to just calculate determinant of this matrix. So determinant of this is equal to because here is minus, so multiplying this with minus sign, I've changed the sign here to plus. Okay, can you see it? And let's leave brackets. Minus A1, C1, A2, C1, 2. And here you can see this term disappears. And I will obtain A1, A2, and what's more, C1, 2, C1 minus C1, 2, C1. Okay, so determinant looks like this, but probably you remember the formula for sinus alpha minus beta is sinus alpha cosinus beta minus cosinus alpha sinus beta. And if we if we take alpha equal to Q1 plus Q2 and beta equal to Q2, you can obtain this formula. So we have A1, A2, what? Sinus Q1 plus Q2 minus Q1. So finally, A1, A2, sinus 2, okay? So what we have, determinant of Jacobi matrix, in this case is equal A1, A2, sinus 2. So singular configurations so because A1 and A2 are lengths of links, so we can assume that they aren't equal to 0. So determinant is equal to 0 when S sinus of Q2 is equal to 0. So Q2 is equal to what? 0 or Q2 is equal to pi. Of course, Q2, we are assuming that it belongs to a range of 0 to pi. Okay, so singular configurations in this case are the following. Please notice that configuration is singular. I've selected only Q2, so it must be here 0, Q2. And what about Q1 value? So can someone try to answer this question? What about Q1? An idea? As can you see, which values of Q1 are good to satisfy this property? No one can help me. I can plug here any value. Usually it is marked with a star. So singular configurations are any value of Q1 and 0 value of Q2. And any value of Q1 and pi value of Q2. So in this example, I also make once again drawing of this situation just to illustrate the concept of configuration space and how singular configurations look like. So you know, task space is just all point X So task space is all points X when Q belongs to configuration space. In this case, let's example Q1 belongs to 0 to pi and Q2 belongs to 0 to pi. Okay, so we have a manipulator like this here. And the task space, we need to set all points X, maybe like this. So the question is, if I can change Q1 and Q2 as I like, according to the rules, so where all points of n of f factor will be drawn in this picture. Can you imagine what would be the shape of all points, sum of points appearing when Q1 and Q2 is changed?
It would be a circle.
Circle. Oh yes, please write your name in a check box.
I would say that it would be a circle for node 1, and for the end of the effect, like again circles on the outline of our circle of node 1.
Okay, so the answer is you also write your name. So the problem is quite simple. Let us assume, just to fix our attention, then Q1 is equal to 0. So we have manipulator like this, and we allow to move only Q2. So as can you see, we draw here a circle, okay? So for sure, we have this point, okay? and also these, and these. And let's move this circle, moving Q1. So let's concentrate on a shape of this point. This point, okay? So when Q2 is equal to pi, so the manipulator is fully stretched. And if we rotate with Q1, so you can easily imagine that I will get a circle. Oh, maybe not very. So let's discuss the radius of this circle. Can you see it? Is A1 plus A2. Okay, can you see it? Okay, but what would be image of this point if I try to rotate it by Q1? So what it would be? Can someone help me? It would be also a circle. Okay, but a little bit more complicated case is what would be the radius of the circle. So it is worth of plus. So please help me and decide what would be the radius of this circle.
I think it should be A1 minus A2.
Oh, in this case, yes, but generally, please, what would be if A1 would be smaller than A2? So we have the situation like this. The first link is very short and the second is very long. So the answer is the following. We need to take absolute value of the two values. So we have task space in this particular case looks like this. Okay, so we have two circles centered at the same point. The outer radius is A1 plus A2, but the inner radius is absolute value of A1 minus A2. And in this context, let's have a look where are images of singular configurations, okay? As I've mentioned, singular configurations look like this. So let's examine these. Let's take a value of 0 here, and we will obtain this point, as can you see. If I take the value, let's say 10 grads, so I will obtain this point. So if I change Q1, so I will get this shape. Oh, not this one. So the outer circle. Please notice that the image, it is the image of singular configurations. Why? Because singular configurations live in configuration space. And here you can see task space. But nevertheless, image of those configurations forms outer circle. And those configurations forms inner circle. So it is quite frequently in robotics encountered situation when singular configurations, when mapped via forward kinematics, are somewhere at boundary of a task space, okay? And let's make one more characteristics of configurations. So one more question. Let's draw which maybe this color. I have a manipulator. It's such configuration like this. Okay. What can I say about this configuration? I'm asking, could, by changing angles, I mean this angle and this angle, can I move this point in any direction or not? What's your intuition in this case? Can I do it or not? Of course, using very small motion. Can I do it or not? What's your opinion on the subject? Let's try for your own. You have a planar pendulum, and you are at such a configuration. Can you move in any direction or not? For sure you can, but if you are fully stretched, okay, like this, maybe like this. So could you move in this direction without bending your ankle? Probably not. So it is quite visible difference between regular, here you can see regular configuration, and here is singular configuration. At singular configuration, some motions at some directions aren't allowed. But in a regular configuration, you can move in any direction, and therefore you will not have any problems with Newton algorithms. Okay, so let's conclude today's lecture. We will back at our next lecture just to complete some details, but let's conclude this. We started with inverse kinematics. We have discussed ingredients of inverse task. I mean, we are given kinematics, so expression for kinematics, initial configuration, and goal point. And we try to find configuration such that the configuration is plugged into kinematics. It results in given final point. For non-redundant manipulators, we are using Newton algorithm, which allows us to calculate consecutive configuration based on this equation. And the algorithm needs to calculate Jacobi matrix, and Jacobi matrix is quite easy to calculate. And it works quite well only in the case when this matrix is invertible. So in our terms, it works quite well when consecutive configurations are regular. The algorithm is stopped when we are close enough to the destination point. Of course, we need to set a threshold, a given accuracy. It is maybe 1 millimeters, for example. Unfortunately, we have two problems. The first problem is what to do when manipulator is redundant. So the matrix, Jacobi matrix, isn't square matrix, but it is rectangular, and we cannot directly inverse this matrix. And what to do when matrices, I mean Jacobi matrix or the other manipulability matrix, cannot be inverted. And here I've illustrated that for redundant manipulators, we have lots of solutions, and we need to select single of them. And we usually use pseudo-inverse of Jacobi matrix, which selects the solution which is as close as possible to the origin of configuration within configuration space. Okay, and Newton algorithm of inverse kinematics for non-redundant manipulators looks very similar to previous one. The only difference is that instead of inverting Jacobi matrix, we are using pseudo-inverse, and the pseudo-inverse is based on Jacobi matrix, but of course it is a little bit more complicated. Here appears so-called manipulability matrix, and we can find whether this matrix is invertible, but by examining manipulability index. When manipulability index takes the value of 0, we are sure that this matrix cannot be inverted. Okay. And then I've illustrated on a few examples how to calculate rank of a fixed matrix. Okay. So the concept of rank of matrix is quite easy, and then I've generalized it into configurations, and I've called configuration Q regular when a rank of the matrix is maximum possible. And of course, it is singular, configuration Q is singular when rank of matrix drops below its maximum value. And I've calculated a single example, well-known double pendulum. I've calculated Jacobi matrix, calculated the determinant of this matrix, and if I compare the determinant of this matrix to 0 and calculate all configuration which satisfy the equation, I've obtained a set of singular configuration. Please notice that those components of Q vector which aren't present in this equation could take any value, in this particular case Q1. Then I've recalled what does it mean task space, and we've noticed that usually singular configurations, when mapped via forward kinematics, occupy boundaries of task space. It is quite useful observation. Okay, so it is all for today. If there are some questions or comments, so please state them right now. If there is no question, so thank you for your attention. I will send the PDF file of this presentation into ePortal very soon. So thank you and bye-bye.
Thank you. Goodbye.
simplified model of the amplifier. You can see here the base emitter junction. This is the